we've basically introduced the fundamental ideas and fundamental concepts of this world of electricity. And you remember there are two sets of fundamental quantities, right? Some vector quantities and scalar quantities. So I will start from that. So vector quantities, you remember we introduced the electric force, then also electric field as the force divided by the value of the probe charge. And then at some point we decided to switch to the scalar quantities. Instead of force, we introduced the potential energy, electric potential energy. Both of these quantities describe interactions. So pretty much we're replacing quantity with a similar quantity. And we're not replacing apples with oranges, right? Then, instead of electric field, which describes electrical aura, we introduce the vector quantity, the electric potential. Again, they describe the same thing, but vector quantity and scalar quantity. Then, of course, fundamental formula how we can find electric force. If you have a charge exposed to some electric field, Q times E gives you force acting on the particle which is exposed to the electric field. Similar, if you have a particle exposed to, again, electrical aura and you know the value of the electric potential, charge times the value of the electric potential gives you potential energy. Right? Okay, then, so for particular systems, point charge and parallel plate capacitor, so all these things. So force for, of course, Coulomb's law, interactions between 2 point charges. Of course, we all know that, KQ, Q over R squared. Then, if you replace electric force with the potential energy, we derive it, and we got this formula. Potential energy of these interactions, so KQ small times Q capital divided by R, first power of R. Again, vector quantity, scalar quantity. And then, if you introduce electric potential, you just basically need to remove the value of the probe charge. You will get the electric potential at this point created by that point charge Q capital. It's a KQ capital divided by R. So, very important things. Of course, we're going to use it. Then, if you have now a system of a capacitor, which give us a uniform electric field, right? So, of course, if you want to find the force, let's say you position point charge in the inside of the capacitor, of course, force can be found Q times E. It's essentially the same. Then, if you make a transition to the potential energy, Q times the value, this is the value of the electric field, times X. X is a distance to the point charge from the negative electrode. You remember that in your quiz, recent quiz, you had to use that idea, right? And, of course, this part, E times X, it's essentially the electric potentials, right? So, if you take potential energy divided by the Q, potential energy divided by the Q, Q disappears, and you have the expression for the electric potential, right? So, we used it just recently. And then, also, we introduced an alternative way of finding electric field, Gauss's law, right? So, you can use this to find the electric field, or you can use Gauss's law. So, if you have some charges, you can pick any, literally any, closed surface, but it must be closed. So essentially, it's a closed surface, not some closed loop. And so if you calculate this integral, which is essentially flux, electric flux, through your chosen Gaussian surface. So that flux must be equal to the total amount of charge enclosed by that Gaussian surface divided by our universal constant epsilon naught. And Q enclosed, in this case, it's a charge 1, 2, and 3. Charge number 4 is outside. We're not counting any charges outside. Okay, so that is also definition of the electric flux. In the simplest possible case, E dot A. This is in general. This is special case. Okay, and the last piece which we need for this exam, properties of conductors in the electrostatic equilibrium. So we spent like 2 classes discussing that. So if you have a piece of metal, first of all, they have tons of free electrons. They're free to move anywhere they want, or you want. And we found, so if you are exposed to this piece of metal, no, if you dump some amount of charge or expose it to some external electric fields or something like this, right? So then electrons will move and distribute themselves in such a way to make electric field inside 0. Otherwise, electrons will never stop running, they will keep running and running and running to make net electric field inside 0. So then, if there are any excess charge on the conductor, that excess charge must reside on the external surface of this conductor. Right. Of course, distribution can be complicated, but that's another story. And then, since we also introduced the electric potential, we also just recently we proved that in the state of electrostatic equilibrium, electric potential inside of the conductor must be constant. Electric field 0, electric potential constant. Right? Okay, so that's basically the scope of first exam. All right, okay, so let's start moving. So usually it takes like about 2.5 hours to cover all these. So we started with introducing electric force and electric field. So let's just quickly review. And you remember the tedious problem when we spent like almost the whole class adding vectors. So let's just go through that quickly at the very beginning. Let's add vectors, just to review vector algebra. Right. Because it's one of the essential parts pretty much throughout the whole semester. We keep adding, subtracting vectors. It's almost everywhere. Okay, I will probably use just only this part of the whiteboard. And let me call it problem number 1. Right. And first, okay, let me introduce coordinate system. First, this will be y, then x. Right. Okay, maybe I should make it longer. Right. Yeah. I remember I wanted to say something. If you have any questions at any moment of time, just ask, say something quickly, right? It's our free time, right? So we don't have to be here, we don't have to be official, right? So, and I'm sure that after your question, I can easily go back and continue. All right. So let's assume that we have two charges. One is positive and one is negative. Let's position the negative at the origin, right? Charges Q1, it's 10 nanocoulombs. Again, prefixes are given in the formula sheet, so you can see them. And Q2 is minus 10 nanocoulombs. Essentially, it's a dipole system. Plus Q and minus Q. It's a dipole system. Right? And so some geometry is given. So let's say this is point x equals 1. And this, x equals 1. So, of course, everywhere there will be electric field created by this charge, by that charge, essentially a superposition of two fields. Right? So let's just pick any point and try to find the net electric field at any point. Of course, you can pick any literally point. In my example, I picked this point, which is at y equals 2. So this is point 2, somewhere over here. Let's say it's 1, and this is 1. Right, so this point 1. Okay, so this is the point in question which we want to analyze. So let's say point P. So we need to find E net at point P. Right. Electric field? Yeah, components. We're going to find components. You remember, it's like the problem which we solved in the class. And again, we're not going to discuss anything new, just reviewing, refreshing. Right? So, first of all, every time I push you guys, even in the graduate level courses or up on the graduate level courses, picture is like 30% of the solution. Right? So draw in this case, especially if you're dealing with vectors, draw vectors. So then, again, based on the quiz number 1, guys, it's like work culture. So, of course, you can draw a vector anywhere you want as long as you preserve its magnitude and direction. But in this case, it's much more convenient. If you want to find net field at this point, draw all the vectors starting from this point. It's just easier, convenient. If you draw them somewhere, you can draw them here, here, right? It would be correct, but people would look at you. Probably you didn't do well in your classes, right? Because it's not convenient to draw them in some places, for example, connecting to this charge or that charge. Connected to the point where you want to find the net field. Okay, so this charge, Q1, creates the electric field. What's the direction of that electric field at this point created by this positive charge? Yeah, of course, away. Right, of course, away. So let me draw. Use the blue. So this will be E1, the first vector. Right. Okay. So you see, I attach it to the point in question. Then, black. What's the direction of the electric field created by by the negative charge at point P? What's the direction of the electric field? Yeah, Dana. Up. It's an negative charge. You remember, electric field lines all the time, they end on the negative charges. So, of course, in this case, it's down. So this will be my E2. Okay. So now, complete the picture. We just need to add them graphically, just to have a complete picture. But to solve the problem, even this picture is enough. But still, I usually prefer to complete what is called a parallelogram, right? And again, be careful, right? So make sure that it's more or less symmetrical, again, based on your pictures in the first quiz. That's what I'm telling. So this side must be parallel to this, and this side must be parallel to that. Create a parallelogram. All right. And so as a result, the net electric field will be somewhere in this direction. Of course, we cannot guarantee because my picture is definitely out of scale. I didn't look carefully what's the value of the charges, what are the distances. It's just a schematic diagram. Okay, so we need to find this electric field. This is our unknown. Right? Okay. And you remember the procedure exactly the same like what we did in class. So first, let's find the magnitude of E1, then components. Magnitude of E2, components. So as a result, you have x and y component of this vector, x and y component of that vector. So to add them up, you just need to add corresponding components, and that will be those will be components of our net field. Yeah. So let's do it. Okay, I will probably start here. So magnitude, I will put the first bullet. Magnitude E1, it's K Q1, and I will put immediately the sign of an absolute value. Because can the magnitude be negative? No. Because why I keep asking this? Of course, I understand for majority of you, it's kind of stupid, silly question. But again, since I see every semester plenty of students, okay, plenty, I mean 10–15%, find the negative magnitude. So that's why I keep pushing, right, to make sure that you remember that. So magnitude can be only positive and divided by the square of the distance. Let me call it R1. So essentially R1, it's this distance from the charge to the point P. So this is R1. Right. So of course we can easily find the magnitude of this. Okay, no, not the magnitude, just the value of R1. It's a Pythagorean theorem. This distance is given. You see it's a x in meters. Okay, now when we came to this point, I realized that I didn't show that piece of information. All right, 1 meter, and this distance is, again, y is in meters. All right. So Pythagorean theorem, of course, I'm not going to ask you. So R1, it's a square root of 1 meter squared plus 2 meters squared. So it will be square root of 5 meters. Right. Yeah. So I will close my explanation box. Right. And okay, I'm not going to plug numbers. Right. It's understandable. Yeah, I will skip plugging numbers. So if you plug, and I pick the numbers in this case properly so that everything gets cancelled, you will get 18. You remember? I keep bugging you about the units from the very first class. So what are the units?
Sorry. Hold up. I know this one.
Yeah. You remember how we introduced the electric field? It's the value of the force acting on the probe charge divided by the value of the probe charge, right? So it's newtons over coulombs, right? Or since we already introduced volts, or volts per meters, right? So it's a newtons per coulombs or volts per meters. Of course, those formulas are given in the formula sheet. Right? So, and again, if you don't remember some special units, at least write down all the units which you see in the formula. That in that case, I would never be able to tell, come on, you are wrong. Right? So you wrote the right thing. You just forgot about the special unit for this or that quantity. Right? It's just a save. OK, so now that's the magnitude. So now we need to find components. So we need to introduce one of the angles. Which angles, it's up to you. In my notes, I think I picked this angle, basically relative to the horizontal line. So I picked this angle theta. So let's introduce theta. Right. And of course, we should be able to find that angle easily, right? This angle is theta. And of course, what about that angle and this angle? This angle and this angle, graphically. They're the same, right? They're the same. Because this vector and this line, they line on the same line. Right? So, and this is horizontal and this is horizontal. So if this angle is theta, that angle must be also theta. So theta, and now, of course, we should be able to find this angle. Right? Tangent of the angle in the right triangular, it's a ratio of what and what? True. But since we don't have sine, it's not going to give us anything. So in this case, the ratio of the sides. Tangent of this angle, it's a ratio of which side versus which side of the triangle. Yeah. Opposite versus adjacent, opposite versus adjacent. I think that is not given in the formula sheet, right? So okay, you already, maybe some of you freshmen, but it's not your first semester, so at this point, everyone should remember that. So yeah, tangent of this angle, it's opposite side, which is this distance versus adjacent side, right? All right, so tangent of theta, it's 2, which is opposite versus 1. Everyone see that triangle? Okay, good. So, of course, you can take easily inverse tangent, and I will just look at my notes. It will be 63.43 degrees. I just keep more sig figs. And on the exam, I'm not picky about sig figs. But of course, if a problem, in the problem, I know 2 or 3 sig figs are given, and you're giving me 15 significant figures, whatever you can see in your calculator, right? So of course it's not cool, right? So don't make. But of course, if it's a 2 or 3 sig figs, of course I'm not going to do anything. But if you, instead of reasonable number of significant figures, give me a huge, of course I will.
Could you just break down like the first vector for the electric field into like I and J components?
That's what I'm doing right now.
But could you like calculate it like the KQ over Rx and then Ry?
KQ over Rx. No. You have to be very careful. No. First, you need to find magnitude. I saw in the past some students try to find immediately components using here Rx, Ry. So no, that is absolutely wrong. It's a pure imagination, right? So that's not how nature works, right? Maybe in some Hollywood world it would be correct. Yeah, but I've seen it. So careful, guys, right? So first find the magnitude, follow the traditional steps, right? Sometimes when I see something new, and sometimes my brain goes blank, kind of, because you've never seen this before, right? So it's kind of what I'm looking at. It's like I remember my first time I was teaching graduate level classical mechanics, and one student, for the first time in my life, I saw a student found X and Y component of the potential energy. For the first 30 seconds, I was just staring at that without being able to understand what I'm looking at, because it's a scalar quantity. Which components you're talking about, all right? So yeah, then of course my brain kind of calmed down, and I realized it's absolutely nonsense, right? So, okay, but again, it happens. Right? So we found angle. So now we should be able to find components easily, right? So let's find x E1x equals to, of course, it's a magnitude of E1 n times which function, sine or cosine? Oh, yeah, Nicole, go ahead. Cosine, yeah, of course, since we want to find this adjacent side, which is adjacent to the chosen angle, so of course cosine function, right? Cosine of theta. And of course, you see the gap between sine and this first symbol. I left that gap for what? Do you remember our discussion in the class? Is it negative? Yeah, you remember. We use, at least I decided to use convenient angle, but not conventional. Conventional angle would be that angle. If I drew this line, this would be conventional angle. And if I use cosine with that angle, minus would pop up automatically. Right? But since I don't use conventional angle, I don't like angles larger than 90 degrees, sorry. Right? So I use convenient angle, so as a result, I have to pay attention and make sure that my pluses and minuses correct, and I have to do it manually. Or use conventional angle, which is from the positive x direction in a counterclockwise direction. Right? So, and then, of course, cosine, which gives us x component, will give you the correct sign. So I will put minus, because this component, maybe let me draw it here. So this is the negative component. You remember our discussion in the class, right? So great. Again, magnitude we know, angle is given, so I will write down immediately the answer. So it will be negative, where is it? Yeah. 8.05 newtons per coulombs. Right. I'm so bad, I remember. And I keep bugging that particular student until I see that the answer is just flying out of that student basically in no time, right? So you're not the first one. Right. So now E1y, right? So now, of course, we must use sine function, right? And now component is positive or negative? It's positive because it's in the positive y direction, right? So this is the component I'm talking about. So of course it's positive. So it's a plus, and again I will just write down the answer immediately. 16.09 newtons per coulombs. Okay, so that's the components of the first vector, the first set of preliminary results. Right. And now we need to do the same with E2. So again, I will put the bullet, E2 equals K. And again, now the second charge is negative, so make sure that you put a sign of an absolute value, right? Because that's how students get negative magnitude of electric field. And R2 squared. R2 in this case, it's at this distance, which is 2 meters, so we don't need to do anything. Right? So let me show in my explanation box, R2 equals to 2 meters. Okay, so again, I will just write down immediately the answer. It's 22.5 newtons per coulombs. Again, don't forget those nanos, 10 to the power of minus 9, because yeah, that's what students sometimes forget. And again, don't forget to square. Right? Again, that's another place where some students make mistakes. All right, so 22.5, yeah, that's correct. And now components, E2x and E2y. Right. So x component, what's the x component? 0. X component of this vector E2, you see? Yeah, that's why we need a picture, because you see immediately that the x component is 0. Right. And so if this is 0, then the whole magnitude is in the y direction, so 22. Right, so what did I do wrong? Negative, right, absolutely. Right. Minus 22.5 newtons per coulombs. Right. Okay, so that's the second set of components. And so finally, we just need to add them up as vectors. Right. So the last bullet, so E, I just label it as E net. Okay. It will be E1 plus E2. This is the vector form. And of course, we need to write it in a component form. Right. So E net x, it will be E1x plus E2x. Okay, so x components are, this is easy. This is 0, so it's pretty much this whole thing, negative 805. Right. So it will be minus 805 newtons per coulombs. Right. And y component, of course, E1y plus E2y. Oh, no, I'm not going to add them. I will just look at my notes. And
No, never mind. Just calculate in my head.
ah,
Go ahead.
okay, minus 6.4, negative 6.4, yeah. Newtons per coulombs. Okay, so pretty much at this point, it can be enough, right? So we have components, pretty much you know everything about the vector. Of course, it's possible to ask for the magnitude of this net vector. But of course, magnitude will be trivial, right? So it's just a Pythagorean theorem. So magnitude. So what we found right now, it's this is the x component, right? And this is our y component. Actually, is my yeah, actually correct. Both of them negative. So I am more or less in scale. My picture. So my numbers actually matches my picture. So you see, just a right triangle. So x component plus y component, and square them and take a square root if you want to find the magnitude. Okay, I actually didn't do it in my notes because I was not planning it. Okay, you see, it's quite straightforward. Tedious, a little bit tedious. I understand. Right? That's why we introduce all those formalisms which are based on the scalar quantities, because it's tedious to deal with these vector quantities. Okay, any questions? Yeah, I expect that. All right, so now let's answer a couple of conceptual questions. Right. So what if we have this situation? So it's, how should I label it? So that was 1, so let's call it, I don't know, 2.1. So that was problem 1, now this is 2.1. So what if we have this situation? We have this electric field. So that's E. Right. And then let's take a electron, sorry. So E minus electron. And shoot it with some initial velocity v naught. That way. Yeah. And so now we need to answer the question, which trajectory are we going to observe? So trajectory, let's say this A, or trajectory B, or trajectory C, or trajectory D. It looks like you started thinking already. Okay, this antenna is annoying. Yeah?
Is it going to follow C?
You think C, right? See? Following the trend? Or see? See? Yeah, so in order to answer the question what happens in terms of trajectory, we need to know the information about the force, because the force is going to either change kinematic parameters or deflect change the trajectory, right, from the straight. So the force, of course, you all remember, F equals to Q times E, that fundamental formula for the electric force, right? So electric field is up, but this is negative, so I can write it like this, Q times E, right? So because of that minus, electric field is up, so electric force will be down, right? Electric force will be down. Actually, it was in your makeup quiz. Yeah, I forgot that. All right, so this will be the direction of the force. Of course, that force, and because of the inertia and initial velocity, so the superposition is going to give us, of course, trajectory C. Right? Okay, so now let's imagine this situation. You are an experimentalist, and this is your experimental setup, and you can change anything you want. So what can you change in order to get, for example, you can change anything. You can use any particle. You can do anything you want with the electric field, right? So initial velocity. So what do you have to change in order to get, for example, trajectory A? Which charge you will have to? For example, yeah, if you use the proton, of course, a proton, positively charged particle, so electric force will be up, and trajectory A is going to be as a correct. Then what do you have to, actually, what else can be done? Let's say you ran out of protons. You don't have a source of protons. What else can be changed? It will be just a less steep or more steep. This curve is going to be that parabola, but you're not going to get a trajectory A. Yeah, you can change direction of the field. If you flip the direction of the field, of course, electrons will fly that way. Then what do you have to do in order to get trajectory B? It's a straight line. Of course, too easy, right?
Yeah. Like
Particle without a charge, one option. Neutron, for example, right? So we have the whole reactor over there, the source of neutrons, right? Tons of them. Right? So neutron, for example, can be used. Or, of course, you can just turn off magnetic field, electric field, sorry. Right? So, of course, all the particles are going to fly straight. Okay, what can you do in order to get trajectory D? Why not? I have weird desire to move my particle straight up. So what about initial velocity?
It's the rate. It gives it like kinetic energy.
But I want to hear a particular word, and you're not pronouncing it. That's why. Ella? Yeah. I'm looking. I have a weird desire. I want to move my particle straight up, or straight down. Let's say.
Bottom right electric field would roughly move it upwards.
No, it's easier, guys. What if the initial velocity is 0? Of course, it will. If it was a proton, of course, it will fly up. If it's an electron, it will fly straight down, right? So, very simple. Okay, just for fun. All possible situations, right, which you can get out of this. Great. So now, what if we have this? Let me call it 2-2. Let's say you have some charged point mass. Okay, just ball charged. And you attach it to the cord and connect it to the ceiling so that it can move, swing. Okay, let me draw the picture. So what if we have this situation, 2, and you apply electric field horizontally. But we don't know if electric field this way or that way, right? And let's say we took, as I said, our point charge, attach it to the string, and let's say our charge gets displaced to this. Right, so let's say this is our Q, right? And what we know that this is, let's say, positive charge. Okay, why not? Let's simplify. Right. So we have this situation, and we know that the electric field is horizontal, but I don't know if it's from left to right or from right to left. But we see this outcome of the experiment. So what can you say about the direction of the electric field? Is it this way or that way?
This one?
You think it's this way, right? Okay, so what? He believes that way.
I changed my mind.
You change your mind. He also was that.
What?
the way. Okay, okay. Now let's start analyzing. What do you think? This way? Okay, so let's start thinking. So here we have a static equilibrium, essentially, situation, right? So it's the end of physics 1 class. You remember you were stabilizing bridges, right? Some bars, right? So with some ropes, right? Okay, so it means that we need to look very quickly at all forces acting on this point charge. So forces. There is a chord. As a result, which force? Tension. Physics 1. Tutoring or whatever, laying. So of course, tension force along the chord away from the object. So tension, the first one, Ft. Then of course, ubiquitous gravitational force straight down, mg. And then as a result, in order to have this stationary situation, the electric force must be pointing in which direction? In order to balance all these forces in the x and the y direction. So what should be the direction of the electric force? Of course that way. Because if the electric force this way, you will never be able to balance the forces in the x and y direction, right? Maybe in the y direction, but in the x direction, never, right? So of course, electric force must be this way. And since our charge is positive, right? So, and you remember the formula, F equals QE. So in this case, since charge is positive, direction of the force and direction of the field must be the same. The same, not must be, the same, right? So it means that electric field is actually to your right. Let's erase this. Right, so this is the direction of the electric field. Right. Okay, it's just a simple conceptual question. So then, so now let's solve this problem. Okay, so this will be a problem. You know what? I'll probably do it here. It feels like I'm not going to write any formulas as I usually do. Okay, I will erase this. I will just stick to the middle of the whiteboard, this part of the whiteboard. So that will be problem number 3. Right. So let's assume that we have 2 charges which are stationary. Let me draw them here. Let's say this is 4q, and underneath I will write stationary. Maybe we'll try to do something, and this charge might want to go somewhere, but we're holding it. I'll nail it, and somehow we made it stationary. It's not a big deal. It can be easily done. And then here there is a second charge, q, also stationary. Distance between them is L, I think. Yeah, distance between them is L. So what else? Q for QL. And so now let's take the charge number 3. So the third charge. And my question is, where should I position that charge? Here on this line. Let me draw maybe line, this horizontal line. Where should I position that third charge Q? Here, here, somewhere, or there, in order to have a stable situation, so that the net force acting on the third charge Q will be 0. Stationary situation. So should I position that charge Q over here somewhere, or somewhere over here, or somewhere over there? And of course, then we will have to find the actual exact position for that charge number 3. Right. Okay, so what? Let me just write it down. So the question. So we need to find position for Q the third charge so that sum of the forces acting on the charge will be 0. Stationary points. Okay. And that is, you see again, Q, it's like that one. So this is our charge number 1, charge number 2, and this charge number 3. So we don't move this charge, we move charge number 3. Right. Okay, so what about this region? Let's start analyzing first regions, and then once we come to the conclusion of where it is possible, then we will start actually solving the problem of finding the actual distance. So is it possible to have the charge somewhere in this region? And so that the net force acting on the charge would be 0. Is it possible here? Let's imagine. So what if I position, okay, I will use blue charge for that. I mean blue color. Why not? You sort of, you shake your, both forces acting on this charge from this, yeah, of course we assume that they're all positive. Plus, 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 right? We assume they're all positive. So this charge acts on this one. The force will be this way. This charge exerts force on this one, will be also the same way. So cancellation is not possible. So over there, it's impossible to have that stationary point, right? So sum of forces equals 0 is impossible. Okay, so we'll just leave this region. All right, so it's then this, the same story, right? The same story. If I position charge over here, so the force from this will be that way, force from that will be also that way. So again, the same situation, right? So over here, sum of all forces equals 0 is impossible. So it means that most likely it will be somewhere here. Okay, so let's position it, for example, at this point. So force from this will be that way, repulsive, and force from this will be also this way. So let's call it, it's a F2, and this is F1. Yeah, here it is possible. So now we just need to find actual distance. Okay, position for the charge. Okay, so now we need to solve actually the problem. So this is possible. Okay, so now let's create the equation. So let's denote the distance, for example, from this charge to that charge as x, our unknown, right? Okay, so let me introduce this distance as x. Of course, as a result, this distance will be what? Of course, L minus x. Yeah, L minus x. Okay, and now, since we want to find that sweet spot, sum of the forces equals to 0, right? So that's what we want to achieve. So it means that F1 equals to F2. Maybe I should, yeah, I labeled them F1 and F2. They must be equal to each other, right? Coulomb force, point charges, right? Coulomb force. So we can write this as K. F1, it's this and this. So it's a 4Q times Q divided by which distance? X, right? Distance between this charge and this charge. So right now it's a F1. It's a x squared, of course, right? X squared. And it must be equal to K, and both of these charges are Q. Q over, and now L minus x squared, right? Because that's the distance. L minus x squared. Okay, so one equation. How many unknowns? Of course, one unknown. You see x only. The rest is, actually, Q is also unknown, right? So lots of unknowns, but the thing is, Q can be cancelled, right? So these Q's and those Q's can be cancelled. K also goes, right? as a result, we're getting the equation k can be also cancelled. So it's a 4 times this. Okay, let me first rewrite it. 4 over x squared equals to 1 over L minus x squared. So trivial equation. So we should be able to solve it easily. Right. Yeah, I need to take probably square root. Yeah. So it will be 2 over x equals to 1 over L minus x. Right. And now proportion, I can multiply this by this and this by that. So it will be 2L minus x equals to x. 2x, I will move to that side. It will be 3x. So it will be 2L equals to 3x. Right. So x will be equal to 2/3 of an L. Right? Yeah, of course. So x will be equal to 2/3 of an L. So at this point, the charge will experience the zero net force. Of course. So it will be stationary sitting at that point. So just to practice Coulomb's law. Right. So, you know, now probably, okay, you know what I get used to when every time on my left side there is a formula, a whiteboard with all the formulas, so I can go and say what will be next, what we discussed, and now I feel like something is missing. All right. Okay, I found it very, very convenient. Right? So now probably let's just discuss properties of conductors and flux. Right? Properties of conductors and flux. Right? And then Gauss's law and then energy approach. Yeah, let's probably do this way. Okay, let's do this. So now it will be problem number 4. It's sort of similar to your quiz. Quiz number, what I forgot, about properties of conductors. Right? And since you did well, but I thought it would be better. Right. So problem number 4. So what if we have this conductor, right, of this shape, weird shape, right? So that's conductor. Let me even write. So this is conductor. So essentially a metal. Right. And you remember, of course, I will now start drilling some holes, cavities. So let's say we have, I don't know, the first cavity is over here somewhere. Then the second is over here. I was just trying to be creative. Use different shapes. Right. Then, so we have a conductor. Yeah, I wrote it down. Now let's position some charges. The first one, let's position in this triangular hole. Let's call it -2 coulombs. Then in this, you know what, let me first show where the conductor, actually material. So this is the material. And those are cavities. And inside of this spherical hole, it's a three-dimensional picture. Let me position 2 charges. One is over here, let's say +8 coulombs, and then a negative charge somewhere lower. So let's say -3 coulombs. And now let's assume a certain amount of charge inside of the conductor. Let's say conductor is charged, although it can be neutral. Neutral, it means 0 charge. Okay, so let's make assumption that Q total, okay, you know what, let me use the blue over here. So Q total of the conductor is minus 6 coulombs. So this situation. And of course, you remember the questions which we will have to answer. The amount of charge on the first cavity, on the surface of the first cavity, amount of charge on the second cavity, and then amount of charge on the outer surface. Right? Is it possible to have a charge inside of the conductor? Yeah, of course, good. I remember it. So that, it's impossible to have an excess charge. Of course, overall charge is possible, but equal amount of positive and negative charges inside of the conductor. But any excess charge can be only on surfaces. Great. Let me write. So question A, part A. So the amount of charge on this first cavity. Let me label it like this is Q inner 1, the first cavity. Right? So QI1. So what can you say about the charge on the surface of the first cavity?
-2.
Think more.
Is it in the triangle we're talking about?
On the surface? I ask on the surface of the conductor. Of course, I know in the cavity, it's inside of the cavity -2 because it's written, right? But on the surface of that inner cavity.
-8.
Nope. Nope. Easier. Okay, I see how your hand. You remember, this is a conductor. It has a tons of free electrons, which can do anything you want or they want, right? So, and now this, for example, over here, electron, and it sees this negative charge. What will be the response of that electron on the fact that over here there is a negative charge? It will go away. For example, here near the on the surface of the cavity, another electron, it will just go away. So pretty much all the electrons over here will just run away deeper into the conductor, leaving behind what? No. Easy. You remember what is the metal? Essentially, it's in a crystalline structure, and where atoms are sitting, right? Which are positive, and nuclei are positively charged, right? And electrons around orbiting, right? So if some free electrons fly away, then there will be lack of electrons in that part of the conductor. So lack of electrons, it means positively charged or neutral. You see why I'm saying neutral? Because you said that, 0. No, if electrons run away, so that part of the conductor will be positively charged. It lacks of electrons. Lack of electrons, positively charged. Because nuclei cannot move. They're sitting, they're in a crystalline structure, there are lots of forces on them, right? So it's three-dimensional picture, structure. Right? So if electrons run away, this surface will be positively charged. We can say that charge, positive charge, gets or is induced on the surface. Right? And it can be proved using Gauss's law. And we've done it in the lecture, I just don't want it, right? So I don't, and usually on the exam, if you write down the correct answer, I'll accept it. Right? I don't ask for a proof. But you see this simple explanation. Electrons just run away, as you said, and if electrons run away, then of course they're leaving behind positively charged area. Right? Because otherwise it's electrically neutral, equal amount of positive and negative charges. If electrons run away, there will be excess of positive charge. Of course, distribution is not going to be uniform. I drew not very correct picture. But we know that the total amount of charge will be equal in absolute value to the amount of charge inside of the cavity. So it will be plus 2 coulombs. Right? Just changes the sign, absolute value the same, but you need to change the sign. So this will be plus 2 coulombs. Usually on the exam, I expect that you just write down immediately the answer. Right? And again, it can be proven using Coulomb's, Gauss's law. And we've done it in the class. Yeah, you want to say something? I just saw a hand sort of moving up. Okay, sorry. So then, part B. So this, what about the amount of charge on the inner surface of the second cavity?
-5.
Now, just first add them up, right? So it will be positive 5 coulombs. And then, of course, it means that if positive, okay, now again, back to you. So what happens to the electrons? So now you see, inside of the cavity, net charge is positive, plus 5 coulombs. So as a result, what electrons do over here? Of course, they go now, they run towards this surface. But of course, since they cannot jump to escape from the material, so they cannot go through the surface. Of course, under certain conditions, it's possible, but we're not discussing that, right? So they need to have a certain amount of energy. So we assume that they cannot. So of course, that excess amount of negative charge will be accumulated on the surface, right? And in absolute value, the same as the total amount of charge inside, but with the opposite sign. So if inside we have plus 5 coulombs, then on the surface we're going to have minus 5 coulombs. Right? So it will be minus 5 coulombs. Okay, and now part C. Of course, you know what will be the answer. I mean, what will be the question? We need to find the amount of charge on the outer surface. Let's call it Q out on the outer surface. And which fundamental law do we use to answer that question? You remember? Conservation of charge inside of the conductor, of the conducting material. We assume that electrons cannot escape from the conductor, right? And this charge and those two charges, they're not part of the conducting material, so we're not counting them in, right? Although if you add them, if you decide to count, they will be on both sides, on the left-hand side, on the right-hand side, which basically means you can remove them from the equation. So, conservation of charge. In our conducting material. In our conducting material. Okay, so it means that Q total equals to the amount of charge on the inner surface 1. It's like that 3-room situation which we discussed in the class, right? So, or 2-room situation, because charges can be only on the outer surface, inner surface, and inner surface. Inside, it's impossible. So, plus QI2 and plus Q on the outer surface. This is given. We found this, we found that. We just need to solve it for that, right? And again, careful. Even on the quiz, sometimes students try to skip steps. They, without moving, as a result, they start losing minuses or extra minuses. As a result, sign is different. Just careful. Unless you're super confident, then you can skip steps. Q out equals to Q total minus QI1 and minus QI2. Right. Okay, so Q total is -6. Then minus from the expression, and QI1, it's a +2, okay. Then again, minus from the expression, and minus from the value of the charge. So it's a minus 5 coulombs. Okay, so -2 minus 8, so -3, right? -3 coulombs. So you see, it's a well, very similar to what you had in your quiz. Good? Okay, great. So now, another very quickly question. So what if we have some conductor, and let's say over here I position charge plus Q, here charge, I don't know, minus Q, and I ask you what will be the electric field, for example, at this point. Let me write. It's a conductor. And of course, we waited for a short period of time to make sure that electrons finish doing their job. Electrostatic equilibrium is reached. So what can you say about the net electric field at, for example, this point? Or if you don't like this point, I can pick this point. Still not the one. I can pick this point. I can see your hand. Okay.
0.
Again, you remember what's the property of the conductor in the state of electrostatic equilibrium? So electrons over here, free electrons, they are free to move anywhere they want. So they see this positive charge, of course, which creates an electric field inside over here. The electrons immediately start running towards this surface. There will be accumulation of negative charges. And as a result, they're going to leave behind positive charges over there. So as a result, there will be additional internal electric field in the opposite direction relative to this field. And the electrons will distribute themselves in such a way that these two fields are going to cancel each other out inside. Otherwise, electrons will never stop running. They will keep running, distributing themselves in such a way that they would stop feeling, until they will stop feeling the electric field. So the electric field, net electric field, must be 0 in the conductor. But of course, you need to wait for some short period of time, maybe picosecond, maybe microsecond. So electric field. Of course, this charge will do its own work, but we have gazillion number of electrons, enough of electrons to, to run around, to distribute themselves properly, and they will guarantee that the net electric field will be 0. Or if you have a huge influence from outside, then of course, that's a different physics. Electrons start jumping out, creating sparks and so on. Right? So, but we're not discussing that part of physics. So inside of the conductor, electric field must be 0. And based on the new results, when we introduce the electric potential, what's the electric potential? What can you say about the electric potential inside of the conductor?
0.
Nope. 0, it will be very special case. It was like a couple of classes ago, no, previous, couple of classes ago. Just a second. You remember? No? Even today in the morning we used that property. You remember charges were moving from the battery into the capacitor in order to do what? In order to bring all that piece of a complicated piece of a conductor to exactly the same electric potential. So electric potential inside of the conductor constant. 0, it's a special case if your conductor is not charged. But if it's not charged, if it's a negatively charged or positively charged, we have to make a more general statement. Electric potential inside of the conductor is constant. So V is constant. Again, it's an alphabet of electricity, right? And of course, properties of conductors. And the whole electronics, simple, all these circuits based on this fact that electrons keep running until trying to make electric potential constant. And of course, very often in circuits, they just fail to achieve that because of the battery to keep driving them crazy, providing the potential difference. They keep running, trying to make it constant, but because of the battery, they fail to achieve that. Okay, so this should be already in your blood, right, close to that state. All right. It's like AI training, right? You need to flush more and more information, and the more information you flush, the better. So the same, similar with us, right? So that's why you're going to these classes, and we keep drilling you, right, so that you would remember that. And it will be part of your system. You know what? Now, what if? Yeah. Now let's start discussing fluxes. And yeah, I will probably keep this picture, and I will ask another question about this later. So now let's discuss business about fluxes. So that will be number 5. Electric flux, of course. Oh, Vladka, good. More people. In previous semester, I had less students, about like 3-4 students, but by final exam, significantly larger. But this semester we have more. So it's a number 5, as I said now. So what if we assume that over here there is a charge Q, right? And then what if I pick some surface, closed surface. Oh, for example, the cylinder. Okay. Closed surface. As simple as that. So now, if I ask you, what's the value of the electric flux through this closed surface, through this cylinder? What will the flux? Zero. Zero, zero, zero. Why zero?
Because there's no charge on the surface.
Basically, you're subconsciously or consciously applying which law? Gauss's law. Gauss's law, right? So the question is, so what is the flux, electric flux, through this surface? Of course, we use Gauss's law, integral of E dot dA, which is essentially flux, electric flux, right? So it is equal to Q enclosed over epsilon naught. Yeah. So if the question is about flux, just look at the total charge inside. Since there are no any charges inside of the surface, the flux will be zero. So Q enclosed equals 0, so the flux is 0. Good. Now, what if I create this situation? So let me separate them somehow. The same cylinder. Right. The same closed surface. And now, what if I position over here a charge plus 5 coulombs, and over here minus 5 coulombs. And the same question, what about the electric flux? Zero. Zero, guys, or not? Why you were not? Why weren't you very confident? So why are you not confident? The same story. Gauss's law. So again, the question is about the electric flux, and it is equal to Q enclosed over epsilon naught. Q enclosed is the total amount of charge which you can physically find inside of your chosen Gaussian surface. In this case, this surface. So, what's the total amount of charge in the Gaussian surface? Yeah. Plus Q minus Q, or plus 5 minus 5, 0, right? Of course, 0. Right. So, of course, in this case, electric flux equals to plus 5 coulombs minus 5 coulombs divided by epsilon naught. Of course, it's 0, right? And I can add maybe additional charges outside, but outside, who cares, right? So they don't contribute to the net flux. So now, what if, for example, I go back to this problem, the previous one, and what if I create this surface outside? This is my closed surface. So if I ask you, what will be the flux through that closed surface? So if I ask you the question, what will be the flux, electric flux in this problem through that particular surface? What negative? Negative 6 over epsilon naught? Negative 6 over epsilon naught. Actually, let me check. No, it will be slightly more complicated. Huh? He wants to include charges inside of cavities. Is he you were also thinking, right? Yeah, we just need to look at all possible, count all positive, not possible, all the charges which are physically inside of the Gaussian surface. In our case, Gaussian surface embraces everything. So we just need to look at every corner of our system and count all the charges. So minus 6, it's a good start. It's the amount of charge in the conducting material. So all the charges over here on that surface, right? So, but we also have charge over here in the cavity, and these charges, this and this. So in this case, essentially, we need to, it's a -6 coulomb. It's a conducting material. Again, those charges on the surface, they are inside of 6 coulombs, -6 coulombs. Then inside of this cavity, plus -2 coulombs. And inside of that cavity, +8 and -3. Yeah? +8 and -3 coulombs, and divided by epsilon naught. I can, whatever system I have, I can embrace it with something, right? And ask what's the value of the flux. You just need to look at all the charges inside, and that's it, right? So it's not a big deal. And again, Gauss's law, you remember it's universal law. So far, it works everywhere. No one found examples where it would fail to work, right? So you can add them all up. Wait, I haven't done in my notes. Just 5 -6 -1 -2, it's -3, right? -3 divided by epsilon naught. And again, don't be afraid to leave your answers in terms of these fundamental constants, epsilon naught, pi, right? It's okay. It's good. All right, so now, another question. A few times I used in the past exams, and now let's just Okay. Is that also your question?
I was going to ask that, like, given that the Gaussian surface encloses the whole.
Okay. Charges on the outer surface, charges over here on this surface, on that surface. Where are they in this? All these charges on the outer surface, on the inner surface 2, inner surface 1. They are part of our total charge inside of the conductor, right? So we know that the conductor is charged to that amount. And then those charges, some will go to the right, some will go to the left, some will go somewhere, who knows, right? Different gangs go to different places, right? So but we know the total amount of charge is given, right? And then they somehow go to the first term, this is the second term, this is the third, but we know conservation of charge, they all will be there. Right. So they're inside of minus 6 coulombs, right? Make sense?
So if the Gaussian surface was to enclose the whole conductor, then could you just replace Q in with the surface charge because it will always be the same thing?
Okay.
Because the net charge enclosed by that Gaussian surface is just the surface charge that we calculated.
You're saying if the Gaussian surface was on the surface of the conductor?
As long as it encloses the whole surface of the conductor, that would just be the outside surface charge?
No. If it encloses the whole conductor, just need to count, take the total charge of the conductor plus what is inside of this. Again, you can count all these charges on the outer surface, this inner surface, but you will end up with -6. Right? So you will end up with total charge, -6. I don't see the situation where you will have to count only Q outer. Unless you Gauss, no, I cannot. I cannot. Maybe I need to come down, and I can imagine a situation where only charges on the outer surface must be counted. Right. Okay, so now, let me use that part of the whiteboard. I think it's in the field of view. I think it should be enough. This, right. That was 5. Yeah, it's still 5. Let's count it as 5. So it was, let's say, 5.1, 5.2, and then 5.3. I don't know why I like these cylinders. Every time in my examples, I use cylinders. So let me use another cylinder. All right. Maybe because it's easier to draw. And there are several charges. let's say one charge is over here, plus 2 coulombs, and then 2 inside, 5 coulombs and minus 5 coulombs. Okay, I remember whenever I drew this picture, it reminds me something, but I'm not going to mention it. But it reminds me 2 holes for eyes. Anyway, so we have information, this information. Let's say somebody count the total amount of flux through this top surface. You see this, let me call it top surface. Over there will be bottom and the side. Or how did I call it? Okay, wall. Okay, let me use side, whatever. It's not a big deal. So that bottom, essentially, it's that surface. So you see cylindrical surface can be divided into 3 surfaces: top, bottom, and cylindrical wall. Right? So let's say we know that the flux through the top surface, phi. Whenever you see flux, whenever you see phi, it's a flux. In this case, electric flux. So through the top, it's a minus 15 units, newtons times meters squared over coulombs. It's electric field times the area, right? Then we also know the flux through that side, cylindrical wall, which is 10 newtons times meters squared over seconds. So the question is, we need to find the flux through the bottom. A few times in the past, this question was on the exam. Actually, you can see it's basically exam formatting. I just printed it. It's slightly different, all right. But still, if you understand over all these, so you should be able. Okay, flux is an additive thing. So total flux through the closed surface can be divided to the flux through the top, flux through the bottom, and flux through the side. Okay, so let me write. So flux total equals to the flux through the, okay, let me start with the top. Top plus flux through the bottom, and flux through the, it's the end of the day, Friday. Right? And that's what we did, for example, in your quiz number 3 when you apply Gauss's law for cylindrical surface. You remember you divided the flux into 3 integrals and analyzed them separately. So that's what I did essentially. Okay, so this is given. Let me use different color. So this is given, check mark. At the bottom, no, we need to find this. This is our question, and flux through the side is given. So do we know this?
Yeah, we know that.
So what's the flux, total flux through our surface? Well, you know why I ask you, because in the answering previous question you were not very confident. That's why. But although essentially the question is exactly the same almost. So. Of course, yeah. According to the Gauss's law, charges outside, they give us the same amount of positive flux and negative, because electric field lines, they enter the surface and leaving the surface. So flux will be positive and negative, so they cancel each other out. So total flux, the value of the total flux is 0. Yeah. Because inside plus Q minus Q, so the total flux will be 0. So using Gauss's law, right? So Gauss's law. So flux, which is total, equals to Q enclosed over epsilon naught. So it's a plus Q minus, plus 5 minus 5 coulombs divided by epsilon naught. So it's 0. So our left-hand side in the equation is 0. So this is 0. And as a result, we have one equation with one unknown. As a result, you can easily solve for our unknown, which is the flux through the bottom, right? Following? Okay, so now From here, we can find, so the flux through the bottom will be equal to the total flux minus flux through the top minus flux through the side, right? Again, this is 0. And as a result, minus top, it's a minus 15. OK, I will skip units. Units will be at the very end. Then minus again from the expression, and flux through the side positive. Right. So it will be plus minus, so it will be positive 5. Am I right? Why look? So minus from the expression, the value of the top minus 15, so minus 15. Then again minus from the expression, and the value of the flux through the side is a positive 10. So it's here plus 15 minus 10, so it will be positive 5. Right? So it will be plus 5 newtons times meter squared over coulombs. Right? Again, basically, this question you need to mix Gauss's law very quickly with splitting the flux into 3 parts. Actually, I like this question. Again, a few times I gave this question on the exam, but the outcome were like a 50-50. All right. OK, so what's the time? So 1 hour, almost 30 minutes. You know what? Let's first, should we solve Gauss's law problem? Let's just very quickly refresh application of the Gauss's law for spherical symmetry. Right. OK, any other questions about that particular problem? Good? And now I feel like you're more confident with finding the flux, because at the very beginning you kind of gave me the answer, but I didn't feel the confidence. OK, so now let me erase this. Yeah, it should be enough. I bought recently new Wi-Fi microphones, which are much smaller. But once I tried to use them, and battery died in 1 hour. Kind of, wow, no, it's not enough. So I went back to my old Wi-Fi mics. You know what? Also, I think I need to change marker. So let's do it. I think it was in your slides I provided a problem similar to this. So it will be problem 6. So what if we have this system? Again, as I said, spherical symmetry, because cylindrical is much more complicated, lengthy. All right. So then there is a cavity, right? So this is material. Right. This is a non-conducting material. It's not metal. Guys, read careful problem, because very often students kind of are not very, don't read problem carefully. Right. So immediately read conductor. Remember properties of conductors. Non-conducting material, you're not allowed to use, of course, those properties, because they're not applicable. So here it's, I even emphasize non-conducting sphere. Right. So radii. So this is, let's say, A, and this is B, outer surface of radius B. Then, to have more fun, let's position point charge Q at the center. And this conducting shell, essentially, it's a conducting shell, is also charged positively. I rarely give problems with the negative charges. When some, not just a point charge, but objects. And the total charge, let's say Q. Of course, it's a positive. So Q small at the center, Q capital is spread uniformly. And again, let me write it's a non-conducting material. Or just basically shell stuffed with charges. Right, so, and the question is about, we need to find electric field in the, between A and B. So we need to find electric field for R small between A and B. So inside of the material. So probably the most complicated part. Right? And of course, you know Gauss's law, right? We just need to grab Gauss's law and start applying it. Integral of E dot dA equals to Q enclosed over epsilon naught. And of course, this time I will move faster because we discussed all the details in the class. Right. As usual, first step, before you start applying Gauss's law, what should be our first step? It's an excellent question, I agree with you. Q in, you will not be able, okay, I see your hand. Q in of what? Inside of what?
Oh, define Gauss.
Yeah, of course. Well, of course, right now you answered without actually seriously thinking, but once you start thinking about what is Q in, immediately, which enclosed inside of what? Of course, we need to pick a Gaussian surface first. And again, guys, be careful. Look at which region you want to analyze, and of course, your Gaussian surface must be in this region because very often students just draw it, and then I will walk around and I will emphasize, guys, look carefully where the Gaussian surface must be because it's a very common, right? So we're interested in electric field in this region. Of course, Gaussian surface must be in this region because we basically probe the value of the electric field on the Gaussian surface. All right, so again, as usual, we use green color, dash line. It's my tradition, right? So of an arbitrary radius r, right? Yeah, we've done it, right? Okay, and now we can start counting Q enclosed, estimating the flux, because that's essentially what we have here on the left-hand side. So I will start with the flux. Right, so E dot dA. And you remember, first I usually ask students, show me electric field vector and the area vector, because that information helps us to simplify integral and basically take it without taking it. Electric field, and again, guys, every time draw those vectors on the Gaussian surface. Again, it's not wrong to draw them over here, but every time when I see that, it's kind of because we're analyzing Gaussian information on the Gaussian surface. Those vectors should be attached to the Gaussian surface. Again, if you draw them somewhere else, it's not wrong, but it's kind of work culture. So electric field at this point. Yeah, radial. Right? So electric field this way. Let me draw here, maybe here. Oh, a few should be enough. And another thing. Very often, by very often I mean like about 10-15%. Some students just draw the vectors and they don't label them. No, guys, it doesn't work, right? You need to label them, right? You need to show this is my electric field, this is my area vector. Oh, sometimes they're in the same direction, sometimes in the perpendicular direction, sometimes who knows what. So you need to label them, right? So otherwise, immediately, I will, at least half a point or something I will subtract. Yeah, it's a. You wanted to say something? You were just moving your hand. I'm like a frog responding on everything which moves, right? Like frog ready to catch the fly. And so let me label this. And I label. And area vector, you remember by the convention, so it must be point towards the outside. Area vector, and again, it must be also perpendicular, so it means it also radial. So this is my dA. It's not just A, it's dA, because we're looking at an infinitesimally small patch, right? So dA, and maybe here also dA, right? Okay, so now we see the directions, and now I can again open my explanation box. Since electric field is parallel to dA, so the dot product will be equal to, okay, E dA times cosine of which angle? No, easy. So the angle is between these two vectors, 0, of course, 0. Right? Cosine of 0 degrees is 1, right? So I will write 0 degrees, and I will skip, so I will write immediately integral of E dA. So now we don't have vectors. Again, the advantage of this step that we managed to get rid of vectors. So here we have a product of vectors, dot product, and now it's just a product of magnitudes. Right? So, and then next step, using the symmetry of the problem, right? Since we pick the best possible Gaussian surface, the magnitude of the electric field on the Gaussian surface stays the same. Again, not uniform, just a constant on the Gaussian surface. Right. So, electric field is constant, and I will write on the Gaussian surface. Again, it's not uniform because if you step away from the Gaussian surface, if you move closer, what happens to the magnetic field? Value of the magnetic field if you move closer? You move closer to the source, what happens to the field? You don't have to think much.
I'll get stronger.
Of course stronger, right? If something is smelling somewhere, you move away, right? So field getting weaker, right? So the same here, right? So if closer to the source, stronger the field. Farther away from the source, field is weaker. All right, so it's a constant. It means that, and it's a constant factor. So it means that we can extract that constant factor outside of the sign of integration. So we will get E integral of dA, right? Where is my circle in the middle of the integral in that? It's the integral over the closed surface, right? Over here, it's skipped. And of course, the answer for this, of course, you all know. And guys, again, be very careful, because it's very frustrating to see when students use the wrong formulas for, instead of area of the sphere, students use circumference. So area of the circle, and all those formulas are given in the formula sheet, right? So for this level, you shouldn't be making those mistakes, right? At this level, that should be in your brain, like really, really embedded, right? Written on the golden plate of your heart. Right? So 4 pi r squared. R small, right? R squared. Okay, so we evaluated the flux. Yeah.
On the exam, do we have to show all of our stuff?
You know what? Of course, I'm very happy when I see this, right? But if students write at least something, I'm okay, good, right? And trying to be extract from students everything, but okay. Q enclosed over epsilon naught, it should be equal to that according to the Gauss's law. Right. Okay, and now as you said from the very beginning, let's start counting Q enclosed, right? Q enclosed. So, the first charge, which is enclosed. Which one? We have two Q's, Q capital, Q small. It's enclosed, right? It's inside. So Q enclosed will be Q small and plus some additional charge in this smaller shell between surface of the sphere with radius r small and the surface of the sphere with radius a small, right? So plus, let me call it like Q, R, A. I don't know how to label it, I decided. So between R and A. You see the logic? Right. So let's find this. And like we did in the class. You remember in one of the classes we talked about that. So it's all about this formula. Since we have three-dimensional distribution of charges, it's a volume charge density. Volume charge density, rho. It's the Q divided by the volume. In this case, it's any Q, whatever you want to use, but you need to divide it by the correct volume over which that particular charge is distributed. You can use our total Q. You can use something else. You can use, for example, Q over here, but you need to find the correct volume and divide that by the correct volume, right? So that's our formula in general. And now let's apply it for the total charge, which is given. You see this total charge, Q capital, which is distributed over this shell. Okay, the whole volume of the figure. So rho equals Q divided by volume of this sphere with radius.
That would be radius R. So we're still on finding the charge density?
Yeah.
Oh, okay. Then that would be radius B minus.
Yeah.
Radius A minus.
Yeah. B minus A. Yeah. So volume of the sphere with radius B minus the whole volume of the sphere with radius A. We need to subtract whole because the whole is empty, right? It's a B and this is A. Yeah, so this is correct. B minus, yeah. Subtracting volumes. And again, guys, don't even think about subtracting radii raising to the power of 3 and then 4 pi over 3. I see it sometimes, it's wrong. Okay, what I'm talking about, sometimes I see students do something like this. Which is, of course, wrong, right? We're subtracting volumes, right? So we're not subtracting, okay, this is just absolutely wrong, right? And since I see it, like several students per semester make that mistake, right? So don't. And the other way of calculating a rho, we can use Q enclosed. Let me show that Q enclosed over here. That's what we're talking about, right? So it's a discharge. Right. So we can use that. So it will be rho equals to Q. It's not completely Q enclosed. Okay, so let me call it QRA divided by volume. Now volume with the radius R minus volume with the radius A, yeah. Every time just subtract the whole, remove the whole because it's empty. Right. Okay, and since we have uniform charge distribution, I didn't write it, I kind of assumed. Right? So of course, these are the same, equal, not the same, equal. Right. So now we can wait. So it will be, we need to find this. Right. So it's QRA equals to Q and the ratio of these volumes. So VR minus VA divided by VB minus VA. Right. Okay, I solved it immediately. Right? You see what I've done? Yeah, good. Okay, so 4 pi over 3 can be easily cancelled, right? So and you will get the answer. Q 4 pi over 3 r to the power of 3 minus a to the power of 3. So it's a numerator, and denominator, of course, will be 4 pi over 3 b cube minus a cube. So, of course, this goes. Right, we're getting the expression which you used. Sometimes in the right place, sometimes in the wrong place. Right. Okay, so this must go that way. So that's our Q enclosed. Okay, so the final line. So E times 4 pi r squared. I'm just rewriting this again. So now we're back to this level. now we know Q enclosed. It will be this plus this Q small. All right, equals to 1 over epsilon naught, and inside we're going to have Q small plus Q capital and the ratio of these cubes. Four pi r squared goes to that side, and the problem is solved, right? Okay, let me rewrite. I thought about skipping it. E as a function of r equals to q plus q r cube minus a cube b cube minus a cube, and divided by 4 pi epsilon naught and r squared, right? Yeah. It's here a little bit tedious, but again, at this level, it's not calculus even. It's just a simple algebra. It should be able to handle it easily. Okay, a question. And of course, I know I'm going to ask you. What if I change the conditions? What if my Q enclosed will be outside? Oi, Q, damn it, Friday evening. What if my Gaussian surface is outside? What will be Q enclosed? And it's also connected. I think you asked me. No, I forgot who asked me. So what will be Q enclosed?
Q plus small q.
Right? Yeah. If Gaussian surface outside, then this Q small and plus this Q capital. Right? So if Gaussian surface is in this hole, so it will be just Q small. Yeah. Good, 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 good. All right, so I see that you're getting it. So now what's left? So let's just simple conceptual question about potential energy, then a couple of problems using potential energy, and transition bridges between the electric field and the electric potential. Yeah. Again, so you're moving your hands, and every time I interpret it as you wanted to ask something. Sorry. So now let's answer this. It's a conceptual question. Very often I give it among multiple choice questions. So that will be 7. I think in our class we had a similar clicker question. What if we have here negative charge, okay, minus Q capital, and then there's an electron, yeah, flying like this. So this is the electron, E minus, so electron. This is initial position, and let's say this is final position. Trajectory, it's a good enough. Trajectory, no more details is needed. All right, and we need to answer the question, what happens with the potential energy? So essentially, let's say A, okay, let me write the. Okay, let's just discuss. I will send you my PDF files. You can see options. Let's just discuss what happens to the potential energy in time without writing down which options in multiple choice. So we have point charge, point charge. So two interacting objects. Of course, we can introduce potential energy, right? So potential energy. Formula for the potential energy. Again, I feel like where is my formula list of formulas? U equals K Q this. Okay, let me write Q1 Q2 divided by the square of the distance. So it's a formula in general, right? Okay, so now we need to answer the question, what happens with the potential energy? What can you say about the potential energy? Is it positive and negative? And what happens in time? Is it increasing, decreasing? So, potential energy, positive or negative?
Positive.
So we have electron, negative, and this also negative.
Negative.
Hold it, did you say positive? Ah, and I doubt it. Sorry, again, blame Friday. Friday evening, sorry, absolutely correct. Right. So, two negative charges, of course, potential energy is positive. Wow, what I was thinking. All right. Wait, you didn't see this. That's what I told you. I remember when we, when we started moving into the energy approach, force of habit, very often we use Coulomb's law. But usually I spot it like within a minute or two. And of course, it's a first power of R, right? So it was bad. So potential energy is, of course, positive because we have, okay, let me even write now. So it's U equals K negative Q capital divided by R. So of course, it's a positive. And then what happens to the potential energy in time? Is it increasing, decreasing, stays constant?
It's
Increasing. I don't remember. I need to also analyze. Increasing? Increasing, right? Okay, so let's think. So R in this denominator is this R. So R here is larger than here smaller. So R is going down. So R is going down, and it's in denominator. So function is growing. Function is growing, plus it's positive. So yeah, it's increasing, right? So potential energy. U increases. Yeah. Typical question, very often I use it. Can be some charges can be positive, negative. So once I even use some spiraling trajectory. But the same idea. Look what happens with R. Look what's the sign, positive, negative, and then see what happens with R in time. Good. So now let's solve a couple of problems. Discussing trajectory of the particle using energy approach. Yeah, energy approach. And maybe also force approach. Yeah, both. Because on this exam we have both. Okay, so now let me erase this. Even this. So essentially two problems, and then there will be two very simple problems. So let's call it 8. Again, parallel plate capacitor, PP capacitor. Let's say we have PP capacitor. And in this case, you remember, we just use it as a source of a uniform electric field. We don't use it as a capacitor. We just started introducing it as a capacitor. So let me draw the picture. And this is negative electrode, negatively charged electrode. And this will be positively. You see, I flipped. Usually I draw a negative here and positive there. Now, just for fun, I flipped the order. And, of course, electric field from plus to minus. Now you remember that, of course. So it's this way. So electric field. Electric field value is given. E is 12,000 newtons per coulombs. I forgot to ask you, or volts per meters, right? Newtons per coulombs or volts per meters, right? Then what else is given? Spacing between the plates. 40 millimeters. It's quite a distance. Then we take an electron and shoot it from the positive plate. So this is our Q, with some initial velocity v naught. Do we have to shoot it? Because if we don't provide the initial velocity, it will never move by itself because it is attracted by the positive charge and, of course, repelled by the negative. So we need to shoot it. Right? So we shoot it with that velocity. V naught is given. V naught, its initial, equals to, okay, 1 times 10 to the power of 7 meters per second. Again, the world of elementary particles, velocity are gigantic, of course. Okay, so I think that's what is given. So now, of course, the electron is going to slow down, right? Of course, slowing down. So it means that it will travel for some time towards the negative plate. Then at some moment, it will stop. At least we pick the numbers, such a number so that it will not be able to reach the negative plate. Of course, if you provide large enough speed, of course, it will be able to collide. But let's assume that we don't want to do this. So it will come to this point. So essentially, we need to find this distance between the stopping point and the negative electrode. So we need to find this distance. How did I call it? Okay. So that's what we need to find. And in terms of symbols, I need to introduce something else in order to have a nice description. Let me introduce coordinate system. And I'm going to first use the energy approach. So for the energy approach, where do we usually position our origin of our coordinate system? You remember we derived that formula for the potential energy of a charge inside of a parallel plate capacitor. And where did we position our reference point or the origin all the time? And I derived it. Where's the, okay, now I want to introduce x-axis, right? So where do we usually position the origin? Just say it. Positive electrode or negative electrode?
I don't get your question.
I want to introduce coordinate system, x-axis.
Yeah.
And I want to align it somehow this way or that way. And I need to make a decision where is my origin, where should be my origin. Where? Relative to our, you see, capacitor. Left. That's why I'm bugging you. So what do you want to say?
It's always at the negative.
Yeah, because we derived the formula that for the potential energy every time, assuming that the reference point in our origin is at the negative electrode. If you don't do it, then you will start messing up minuses, pluses, some additional distance, right? So you will create troubles for yourself, right? So every time, the origin is at the negative electrode, and that's also the reference point for the potential energy function. So that will be 0, and x-axis pointed towards the positive electrode. And that's why I flipped the electrode, so that to emphasize on that. Right? So that is my x-axis. And then, of course, our initial point. What is the coordinate of the initial point? So you see, we shoot electron from this point. So what's the coordinate? X. More details than x, more than just x. Numbers are given, actually.
40 millimeters.
Or d. I don't want to use, as you notice, I don't use numbers till the very last moment when the final expression. Yeah, of course, it's a d. So, and that's why if you don't choose coordinate system, you'll start missing, it will be a mess. Right? So d. And our final point, let's call it x and f. F stands for final. So essentially, our question mark, it's what? It's xf. So we need to find essentially xf. So let me write that down. So we need to find xf. Right. Okay. And so I think I gave you everything. Let me check again very quickly. Ah, before we start solving problem, what can you say, additional piece of information about the final point? Yeah, it's a turning point, velocity. Actually, yeah, actually velocity is also correct. Started thinking speed or velocity, both will be zero, of course. Right? V final equals to 0. So this is essentially our initial point, right? And that is our final point, right? So, and since this charged particle moves in the vacuum, no collisions, no energy losses, right? Electric force is a conservative force. We can introduce potential energy, so we can use conservation of mechanical energy. It's a second approach which we introduce in this semester. Right? So let's just first solve it using energy approach and then using the force approach. And on the exam, almost every exam I give a problems of this type, or maybe two charged particles moving, but every time I emphasize which approach I want to see. Right, so just follow that approach. If you try to use different approach, we usually subtract 50%, right, of the points, because we want to see a certain approach. Probe a certain approach. Yeah, so energy. So, and again, conservation of mechanical energy. So if you follow this charge, it doesn't matter at which moment you look, the total mechanical energy must be the same. So you can use that factor to solve problems. So of course this will be our initial point because some information is given, and of course that will be our final point because that's the point where we want to find some information. Right? So E initial equals to E final. And now we need to start diving deeper and deeper until we will see all our quantities. Kinetic energy plus potential energy at the initial point, kinetic potential at the final point. Right? So we've done it in the classes, and usually students don't have any serious troubles except for, yeah, if they pick the wrong origin, then they start making mistakes. Kinetic energy 1/2 mv naught squared. Do you remember the formula for the potential energy?
QEL.
Yeah, QEL or QEX, right? So doesn't matter. So U equals Q. Since I introduce X, let's just use X. But again, L is absolutely correct. That's how I derived it. Then final kinetic energy, as you said, since final velocity is 0, kinetic energy is also 0. So let me remove it immediately. Potential energy, it's a plus QE initial. It's a D, right? Okay, let me write X initial and equals to QE X final. Right. And initial, it's a X initial, it's a D, you just told me, right? So initial point, particle moves from here. So it's at the point D. So this is D. Right. And X final, it's, yeah, that's what we need to find. That's our question. How many unknowns do we have in our equation? Just one equation, one unknown. Physics is over now. It's just a simple trivial algebra. Right? So it's already on the right side, so I don't need to do anything. Wow, great, I like it. So now I'm going to also divide the whole equation by QE, so to make my unknown free from any constant factor, right? Factors. So it will be, as a result, X final equals to mv naught squared over 2QE and plus D, right? So I just move this term to this side. I actually not just move, I just flip the equation, right? And this over here, and this will be just X initial D. Right? This term, is it going to be positive or negative? Just logically. It must be negative because this X final must be less than D. Right? Here, you see? So here we have D, and this must be less than D. So this must be negative. And of course, that negative sign must comes from?
Professor, why'd you put plus D again?
Huh?
Plus D, why'd you put plus D again?
So first, I just flip this equation because my unknown is on the right-hand side of the equation, and we usually write unknowns on the left-hand side of the equation. So first, I just flip this equation. So this is over here, and this plus this over here. And then I divide the whole equation by QE. So this will be this QEX. So first I flip, and then I divide it by the same constant factor, the whole equation, each term, right? Yeah, I could have kept this in this form, having my unknown on the right-hand side, but usually we do it this way. And yeah, so it's negative because charge is negative. And let me emphasize. So it's a minus 1.6 times 10 to the power of minus 19 coulombs. Okay, so numbers are given. I will skip it. Skip plugging numbers. So essentially, you will get 40 millimeters. It's a D. And minus 23.7 millimeters. Right, so it's a this and that. So it's a 16.3 millimeters. Right, so that will be the distance to the negative electrode. And again, on purpose, I flipped the order of the electrodes, so that to emphasize, guys, where the origin should be. So that's the energy approach. And again, most of the time, students don't have any significant troubles with the problems of this type. Now, so that was our approach number 2. Now let's quickly apply approach number 1. The first one, solve the same problem. So in the force approach, we need to write down the expression for the force, mix it with Newton's second law, Coulomb's law, Newton's second law, then get acceleration, and then use one of the kinematic equations, if it's possible to use kinematic equations, right? So classic approach. So probably first I will write down, as usual, expression for the force. F equals to QE. I'm not asking you many questions because we've done it many times. And probably let me show the negative sign explicitly, from the very beginning. So minus absolute value of Q times electric field. And electric field as a one-dimensional vector, is it positive or negative? Electric field. You see now, I want to write explicitly electric field. And it's a vector, one-dimensional vector. So this vector, is it positive or negative according to our picture? Of course, magnitude cannot be negative, but the vector, in this case, one-dimensional vector, it can be positive or it can be negative. So what about E? You do know. Right, look, x-axis, this determines the positive direction and negative direction. So that is the positive direction. So our electric field, that's the answer. So electric field, according to our chosen coordinate system, is a negative vector, right? So over here, I can write E times minus I hat. Okay, so minus here, minus there, it's plus. So our force will be is in the positive direction. Positive direction this way, we saw it, we saw it, right? So it's a decelerating because of the force pointing this way, right? So we're getting that mathematically. So absolute value of Q times E and in the positive x direction. Okay, great. So our force now, we just need to apply Newton's second law because it's an equation of motion, universal law, blah, blah. Right, so MA equals to F, so which is Q, absolute value. Now we drop the negative sign because there are two minuses. There were two minuses. E. So acceleration immediately follows, right? So from here I can get acceleration equals as a vector. Mass will go to that side. Q times E in a positive I direction divided by m. The marker is fresh, still smells a lot. Okay, Dana, can we use kinematic equations? Is it allowed? Are we allowed to use kinematic equations? Huh?
Yeah, you're allowed.
Why not? Can you justify it?
Why you're allowed?
Yeah, why is it possible to use kinematic equations? There's a very, very special feature every time I ask about that, because sometimes it's not allowed to use kinematic equations. Kinematic equations, okay, if you don't remember, we derived them. Okay, say it.
Is it because R is not constant?
No, you remember that particular example where R was not constant, but there's a more specific statement. Okay, acceleration must be constant. In physics 1, in the mechanics course, you derive those kinematic equations assuming for acceleration, constant acceleration. That's why sometimes it's good to remember derivations, because you know limitations of this or that formula. So, and that's why through the whole semester, when we before we started applying kinematic equations, I would ask you guys, what is it allowed? Is it allowed or not? Constant acceleration. And in this case, Q is constant, E is constant, M is constant, everything is constant. So acceleration is constant. Yeah, it's good to use kinematic equations. Right? But in that example, actually, next example, it will be about that. So where R is changing, as a result, acceleration is not constant. Yeah, good luck to kinematic equation. I mean, goodbye to kinematic equations. It's this probably fumes right getting me. Okay, so constant. Okay, so kinematic equations. And most likely, which kinematic equations would be the best? You remember I usually tell you,
One without time.
yeah, no time equation. Because look, we don't have information about time. It's not given, right? So, and the question is not about finding time. So it's usually like 99% that most likely equation number 3, no time equation, will be the most convenient. But again, if you mix equation 1 and 2 for the velocity and position, you can also solve the problem, but you will have to make more steps. Right? So yeah, equation number 3. So V final squared equals to V naught squared plus 2a and x final minus x initial. So that's equation number 3. Whew. So let's simplify it. V naught, it's not 0. V naught is restricting the electron, right? So it's not 0. Yeah, V final. You remember? Yeah, it's V final is 0. Good, 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 good. I like when something is 0. When something is 0. Acceleration we found. X final is our unknown, right? X final is our unknown. X initial is D. Right? We are shooting from this point, right? So X initial is not 0, it's D. So this is D, and X final, this is our unknown. This is our question mark. Right. Okay, so V naught I will move to this side with minus. Okay, let me do it step by step. So minus V naught squared equals 2a x final minus d. So 2a can be moved to the other side immediately. Okay, let me do it again step by step. Okay, it's a xx. Oh my god, what did I write? X final. All right, so x final will be equal to d will be with plus, and then minus v naught squared over 2a. Right? Am I right? Right? So this goes to that side, and then this goes to that side with plus. So d minus v, yeah. Right? Okay, so acceleration we have. Now let's plug it. So it will be equal to d minus v naught squared divided by 2. Acceleration q, e, and m will be upstairs. Right. Acceleration is downstairs, so as a result, this q, e will be in the denominator, and m will go into the numerator. Right. So let's compare with this. D And here, of course, we showed minus explicitly. This is a sign that the fact that the charge is negative. And here we didn't show that explicitly. So essentially, of course, the answers are exactly the same. So the same. I don't know, but now I feel like this was a little bit slightly easier than this. Right? Plus, you don't need to keep track of the directions, right? So it's easier. Right? And again, that's the beauty of energy approach. And again, approaches. That's why all these Lagrangian formalisms, Hamiltonian formalisms were developed in theoretical physics in order to simplify the life of the researchers. Okay, so problem which you already almost started mentioning. Getting exhausted? Yeah? A lot? So how about the rest? We're only 2 hours, 15 minutes. My personal record, the final exam for 4.5 hours. The final exam, but again, it was several years ago. All right. Again, guys, if you're getting really okay, I will send you my notes, right? So yeah, you can look at. Everyone thinks that we should call it a day.
I think we haven't had enough physics yet.
Not enough.
No.
Not enough, right? So you see. Okay, if you feel like okay, you're done, right? So you drain. Yeah, you can go, right? So I will send you notes. Huh? No. Ah, okay. Okay. I thought we're having a coup against this dictator, right? Torturing us on Friday evening. At least it's not Halloween week, right? A weekend. I remember we had some exam review sessions on Halloween week before the Halloween. But I usually don't follow about very often those holidays. I don't know when the day exactly. So now let's solve this problem. Again, energy approach, but now 2-point charges involved. So let's start with this. So we have here a point charge Q capital. We don't know that. Okay, let me first put immediately question mark, and then I will explain what do we want to get out of that charge. So, and this charge is stationary. Again, maybe it wants to go somewhere, but we're not allowing it to go, right? So it's stationary. Then, at infinity, let's say over here r equals to infinity, we have what? Proton. So let's call it q small. And of course it's positive. And so we shoot it with velocity v naught. So v naught equals to 1 times 10 to the power of 7 meters per second. Okay, that's our proton speed. Yeah, of course, we also know that this charge is positive. So essentially, let's say at this distance r, there is something valuable, I know, which we don't want to be damaged by the proton. So essentially, the question is, what should be the value of this charge Q capital so that our proton would stop at that particular point? Turns around and fly in the opposite direction. Both positive, because if the negative, then good luck with stopping. You will never be able to stop it, right? So positive, positive. Of course, this charge proton is going to decelerate, so we need to find that amount of charge, which would guarantee that the proton will come to this point with 0 speed, stops for a moment, and of course, then it will fly away. So maybe some treasure over there, which we don't want to be damaged. All right, so let me write the question. So we need to find Q capital, of course it's positive, which would stop a proton at distance r. R given. So that is given. R is, okay. Now I'm also confused myself. Why did I give a number for the speed if the whole problem is solved in terms of symbols? Right. Okay, anyway, so velocity is given, but number is not. Only now I know it is this bug. Again, it's not a mistake, it's just a bug. Right? Because sometimes you want to prepare one problem, then you start changing something, and then eventually it's possible to have bugs. Right, so what is given? Let me write over here. So it's given V naught, R, and Q small, and that's it. Right, that's it. Right. Yeah. Okay, so let's first draw a trajectory. Of course, this proton is going to decelerate, come to this point, and then it will fly in the opposite direction. Right. So essentially, that is trajectory. And again, two approaches, energy approach and force approach. Again, let's start, what are you shaking? So that force approach, yeah, you would know, you wouldn't go there. So let's start with the energy approach. So conservation of mechanical energy, we assume electron or proton flies in a vacuum, so no collisions, no energy losses. So I can write immediately E initial equals to E final. Initial point, where is our initial point? At infinity. You see R infinity. So that's our initial point over here. Let me use different color. All right, so that's initial point. And the final point, of course, will be at distance r from the stationary charge Q capital. Right, so initial and the final point. And like here, now we need to start diving, revealing all the information. So K initial plus U initial equals to K final plus U final. Do you remember the formula for the potential energy of two-point charges?
KQ1 Q2 over R.
Yeah. Which over here I made a mistake with R squared. So of course U equals to K, in this case Q capital Q small over R, right? So that's in general formula. Right. Okay, kinetic energies. Final kinetic energy, 0, of course 0. So let me immediately get rid of this. Right. So kinetic energy 1 over 2 mv naught squared. Of course, it's a mass of the proton, but since the problem is not numerical, so we don't have any numbers, so we don't have to worry about that. Because most of the time we use electrons, and very often you develop the habit of using that mass, and as a result, if it's a proton, we can make it. Of course, I would never subtract any points for that mistake. What can you say about the initial potential energy? This. This. No, you sure? You know, come on. Look, initial point is at infinity. When R goes to infinity, when huge. R is of course, R is in denominator. So essentially our potential energy is even, yes, 0. It's essentially, it is our reference point. You remember reference point for this system is at infinity. It's the most convenient, like almost accepted by everyone, right? So yeah, it's 0. So this will be also 0, and maybe I will write. So U initial equals to K Q and R, which goes to infinity as a result, potential energy is 0, right? So this will be only kinetic energy. Wow, it's nice. Kinetic energy equals to potential energy. So it will be K Q small Q capital over, and now in the final, at the final point, it's R capital, right? So R capital downstairs. So what do we need to find? Q capital. Right. So again, one equation, one unknown. Physics is over now. We just need to solve it for Q capital. This is our unknown. Right? Okay, so from here, as a result, we're going to get Q capital equals to mv naught squared times R divided by KQ, Q small. Yeah.
Wouldn't it be 2KQ? Or does the one have
Oh, yes. So we're solving this, so it will be, yeah. This goes up to, yeah, 2KQ. Yeah. Okay, so that's the answer. Again, it's kind of easier because this energy and that energy is zero as a result. From the point of view, trivial math is simple. So now, Alla, you started saying about 10 minutes ago about what if we try to apply the force approach? So what will be the problem over here?
We can't use the.
No, we can. But, yeah, okay, so, okay, let me finish. Let me allow you to finish what you were saying.
We can't use like 1.5 mv squared.
No. We use it over here in the energy approach. Now about the force approach. Yeah.
I said R is not.
You remember out of that discussion that R is not constant. But as a consequence, if R is not constant, as a result, what was also not constant? I see your hand. Acceleration. So in this case, acceleration will not be constant. As a result, kinematic equations cannot be used. Right? So again, it's not the end of the world. It can be still solved, but it's significantly more complicated than using the energy approach. Okay, essentially what I just said. So force equals to KQQ over R squared. And Newton's second law, F equals ma. So of course, as a result, acceleration is K Q small Q capital over m R squared. And because of this R, as she said, it's R changes as particle moves. So as a result, acceleration is not constant. So no kinematic equations. Okay, basically, we're not allowed to use them. Yeah, again, we would be like, as I keep saying, physico-mathematical criminals are doing that. It's again, it's not the end of the world. It just means that you need to deal with the second-order differential equation. Okay, enough of this. Now, basically, now what's left is very simple. All right, so let's just quickly discuss bridges between the electric field and the electric potential, and then we'll call it a day. So maybe like additional 15 minutes. Yeah, so it will be like 1 hour, 2 hours, 45 minutes, give or take. So let me erase this. So that will be number 10. So what if we have this graph? X component of the electric field, units, newtons per coulombs or volts per meters. Okay. Now you remember, I can see that. Newtons per coulombs or volts per meters. Right. Okay. And then X is in meters, and let's say we have 3 points. 1, 2, 3. 1, 2, 3. And the graph, I think it's something similar to your homework. I don't remember exactly. But so let me first draw a line. Right. So this will be above 3. Right. And this point is what? 200. And this point is minus 100. Yeah. That's the whole thing. So information about the electric field is given, and also some information was given about the electric potential at this point 0. So electric potential at x equals 0 equals to what? Negative 50. And you remember, we need to make a transition to the electric potential. So we need to get information about the electric potential at point 3. So let me write. So we need to find V at x equals to 3 meters. And again, guys, be careful if you see that problem. Sometimes I don't ask, or sometimes potential difference. Let's say you need to find potential difference between sometimes 1 and 3, between sometimes 2 and 3. So just be careful which numbers, right? Because very often students just assumed immediately from 0. And in this case, it is true. Potential is given at 0 point. Right, so we need to find that. So essentially, we need to apply the bridge between the electric field and the electric potential. So we need to use that bridge. Right. Which is, and again, I feel like where are my formulas here on this side? That formula, integral, do you remember? Or area, calculations of the area under the curve. Right. All right, so delta V equals to minus, you know what, let me write explicitly delta V, because I will need it anyway. Again, it's up to you which point is initial, which point is final. That formula is universal for any points. Right? So you can, but in our case, of course, we will pick point 3 and point 0. So instead of writing x equals 3, just subscript 3, which is self-explanatory. And minus integral from initial point, which we picked 3, to the final, initial 0, final 3. Ex dx. Immediately I applied the simplified version of that formula. Right? And again, this is just the area under the curve, right? Again, a few times I saw that, but again, I've never seen it kind of before. It's not this area, because I saw sometimes students use this area, which is absolutely wrong, right? So yeah, I was also kind of surprised when I saw that. So of course we're talking about this area, right? Which we need to find area between the graph and the x-axis. So that's the graphical interpretation of an integral, right? So it's a minus area, and let me label with points. So it's a O, A, B, C, and D, right? Area over triangle of OAB plus triangle area of the triangle BCD. Right, so now everything is clear. So now, since we're interested in this, let's move V0 to that side. Right, just preparing. So V at point 3 will be equal to V at point 0, and minus, again, the area which I just wrote, triangle OAB plus triangle of BCD. Okay, so now that's, again, we've done it in a class, so you've done it in your homework. So, so V0, negative. And again, over here, typical mistake when students kind of don't do diligently, don't move first to that side, getting rid of that minus. As a result, there will be some additional minuses or lack of minuses. Just very, very careful because these mistakes are very, very silly mistakes, right? So that's why I'm doing it, rewriting, make sure that I wouldn't lose anything. So V naught is negative, so minus 50. And minus the area. Okay, so let's start calculating area. Okay, I will probably put a big bracket for before everything. Minus 100. I will skip units. And the base is 1. Right. Volts per meters times 1 meter, so of course it will be volts. Then, then plus area of this triangle, so it will be 1 over 2. Height is 200. And the base is 3 minus 1. And another bracket, this and this bracket. Right. So conservation of brackets. If you open 5 brackets, you must close 5 brackets. Right. Universal law. I still remember my professors emphasizing count brackets. Right. So what are we going to get? Negative 50, positive 200. So it's a 150 minus 150 minus 50. It's a negative 200. Am I right? Right? Negative 200. I'm getting. Let me check my notes. Yeah, negative 200. Yeah. 200 volts, right? Okay, in my notes, just for fun, I also wrote down a function for this straight line and integrated it. You can do it. I'm sure that you can do it by yourself also. Right. You want to say something?
No.
Again, also. All right. You know what? The next example. To move from V to E, you just need to look at the slope and add the minus in front. So you can do it by yourself. You know what, let me, just before you go, the final conceptual question. Again, a couple of times I give this question on the exam. Just for fun, let's discuss that. I keep saying just for fun. It's a Friday evening, and we're doing hell knows what, right, on Friday evening. It's not fun. Okay, let me erase this. So it's a conceptual question. So the final, CQ. What if we have this information about the electric field? So let's say this is the y-axis, and y, okay, this is x, for example. And electric field is given in this form. So we have here a bunch of vectors, then here of the same length, and here. So essentially, uniform electric field, you see? Uniform electric, at least that was my intention. So we have uniform. Okay, and we have 4 graphs representing electric potential, which is supposed to correspond to this electric field. Okay, let me show them. So we have electric potential V versus Y. So the graph is, okay, let me use blue. So is it true that this graph corresponds to this electric field? Or maybe electric potential versus Y. Okay, let me make it smaller so I can fit. Or maybe it's this graph corresponds to this electric field. Or maybe this, again, electric potential versus Y, and the graph is this. Or electric potential versus Y, and the graph is over here. Which graph out of these 4 actually corresponds to this electric field? You wanted to say immediately something? Let me even label. This is no, A, B, C, and D. So 4 options. You think C? Still thinking?
I also agree with C.
I'll say C.
Just following, following the trend.
I was gonna say B because the equipotential line is perpendicular, but this is.
No, you need to remember, these are graphs, these are not equipotential lines. This is the graph, electric potential versus this Y. You see, this is Y.
Electric, it's constant.
So this is also Y, and yeah, everywhere Y. Still thinking, lad. D. You don't know. Okay, let's start thinking. Matt. So first of all, let's use one of those bridges, which we introduce connecting electric potential and electric field. And yeah, you can use even that with the area, but I think in this case it will be probably more convenient to use the bridge which connects electric potential with the electric field. That one, you remember? E, in this case it's a function of y, so let me write EY equals to minus derivative of v with respect to y. Right? You remember this bridge connecting if you want to go from v to e. Okay, let's look at this graph. So what is dv over dy on this graph? It's a slope. It's a slope, and minus in front. Of course, we need to remember. What is the slope of this graph? Slope. I mean, positive or negative? One, it's too much of info. It's positive. Of course, positive. So slope is positive, but we have minus in front. So it means that the electric field must be negative. And our electric field is negative or positive? I forgot whom I was bugging about the positive. I think it's with you about, you remember about the direction of this electric field. Is it positive or negative, right? Vector. Yeah. So now we have electric field, this electric field, positive or negative on this graph? Positive, because y-axis is up, so it's positive. But this graph gives us negative electric field. So it means that this is the wrong case. Then, this situation, what can you say about the slope?
0.
Electric field corresponds to 0 electric field, and our electric field is not 0. Let's skip this. This is also 0, right? Because there is no slope. Slope is 0. So, in this situation, the slope is negative. This is negative, right? Minus in front, it means that electric field will be positive, right? So positive electric field. Then what about, so direction is correct. But what about the magnitude? Slope is the same. So it means that electric field will be the same at every point, right? So yes, so this is the correct graph corresponding to that distribution of to that electric field, right? Yeah, so pretty much you just need to grab the formula and start analyzing. And again, these are not equipotential lines, but yeah, it takes some time. You need to stare and understand what is actually in front. Okay, so instead of that solving the problem which I was planning to solve, we just discussed, it's just a negative slope. Negative slope. Enough. So 2 hours, 40 minutes, yeah, it's regular time.